for financial anomaly detection, normalizing flow for financial anomaly detection, the impact of loss function. Once again, I will tell you, the thing is, you have 10 minutes to presentation, and after that we'll have a question and answer if questions, then yeah, after that we'll move to the next one. So please feel to share your presentation. Yeah, 166 is the paper ID, and it's Amir Rashidi, Rubani Q, and Rashid Hassan.
Yes. My name is Amir Rashidi, and I'm going to be presenting my work for normalizing flow. Sorry, just to be clear, am I audible?
Yes, I'm
Awesome.
able to see, and also you are audible. Thank you.
Perfect. Then let's move on. All right. So yeah, good afternoon, everyone. I'm Amir Rashidi, and I'll be presenting my work for normalizing flows for financial anomaly detection, which focuses on the impact of the loss functions. And in today's talk, I'm going to be kind of going over how different loss functions are going to be affecting detection of fraud detection performance across 3 different data sets. And this work is a joint work with Dr. Robin and Dr. Hassan. And I'm going to be breezing through some of the slides because it was initially intended for 15 minutes, but I'm going to be keeping it short to match at 10 minutes. So today's agenda, we're going to go over the motivation, research questions, methodologies that was used, experiment results, conclusions, and the future works. So financial fraud challenge. Financial fraud is a serious growing problem, and the volume of digital transactions keeps increasing day by day. Fraud is becoming more sophisticated, and the data is becoming extremely imbalanced. And because of fraudulent cases being a tiny fraction of all transactions, that makes traditional supervised methods difficult to apply effectively, and we try to frame fraudulent fraud detection as an anomaly detection problem instead of standard classification problem. So why did we choose normalizing flows? So most traditional approaches either use supervised classifiers or deep learning models like autoencoders, variational autoencoders, GNNs, but they often rely on a reconstruction error on approximate density or approximate densities. But normalizing flows, on the other hand, they are invertible generative models that can learn full distribution of the legitimate transactions and provide an exact likelihood score for each of the samples. And in our setting, we're training only on normal transactions, and then we interpret low likelihood, which doesn't fit the latent space of that was generated as fraud, practically. So the research questions that we're trying to answer here are: which loss function enhancements lead to the best performance for fraud detection using normalizing flows? How does the change of the loss function impact the final scoring? Does the type of the data set impact the performance of the loss function? So our research contribution include a controlled experiment design where we isolate loss function impact by keeping architectural designs the same. And we introduce a novel ensemble loss functions combining complementary regularization objectives. So each of these loss functions that we have, they are basically attempting to regularize the latent space in their own manner. And we provide some guidance on which loss functions suit which data set the best, practically. So our methodology. We're using an 8-layer affine coupling normalizing flows. And how it works is that it builds a series of invertible functions that map the data from X to latent space Z. And the affine coupling layer splits the data into 2 different parts. So the first part remains unchanged, and the second part is transformed and scaled scaled using the first part that was unchanged. And because of this structure, Jacobian determinant turns out to be the sum of the scale outputs, and it makes things computationally efficient and exact. And during the training, we maximize the log likelihood of the normal transactions, and we are teaching the model what normal practically looks like. That's our objective in the training. And during the test time, a low log likelihood is an indicative of the transaction being likely fraudulent. So the loss functions overview. Baseline trainings uses pure negative likelihood, which is the one of the standards density for density estimation, but it's not necessarily optimal for downstream anomaly detection. And we evaluate 11 different variants: the baseline, which is the NLL, and the individual ones that we are going over are L2, VIB, variational information bottleneck, entropy, spectral, and ensemble, which is a combination of the ones that we had, like the combination of L2 and variational VIB and L2 and entropy. So the data sets that we went over are credit cards financial fraud data set, which has over 284,000 transactions with less than 0.18% fraud percentage. And then that one is a real PCA transform data set. And then the PaySim is a synthetic data set, which was generated based off of real data. And that one has over 6 million data points, and less than 0.13% of it is fraudulent transactions. And lastly, the vehicle insurance fraud, which has far less number of transactions, and it's also synthetic, and it has 15,420 transactions, and 6% of it almost is fraud, which is vastly a different data set in comparison to the other data points. And it required a lot of data scaling in order to get the correct set of parameters. So our experiment results. So for credit card data sets, we were able to see that Spectral plus L2 with performed the best with the F1 score of 88.4%. And VIB, which by itself was a singular loss function, performed at 88.3%. And this kind of proved that simpler individual loss functions can nearly match the performance of the best ensemble ones. And the most important point probably here is that majority of the optimization practices performed better than the baseline negative log likelihood that we had. Now, PaySim results. For PaySim, L2 regularization, individual one performed the best one with 73.95%, which is a 7.6% improvement over the baseline. And this data set shows the largest sensitivity to the loss choice, meaning the right regularization can make a noticeable difference. And again, regularized losses outperform the baseline across all of the main metrics. And since this data set had the most transactions, it's probably allowed the deep learning model normalizing flow create the latent space to the best way possible, allowing this better performance and the large deviations, large difference between different loss objectives. And lastly, the vehicle insurance data set was the hardest one. The performance was much lower overall. The ROCAUC was barely above the random guessing, and the best F1 here is achieved by Spectral by 48.59%. And just to clarify, we are using the mean of the F1 for the non-fraud transactions and then F1 for fraud transactions. So we are getting the average of each class, and then we're reporting numbers over here. So going over the research question answers, which loss functions enhancement lead to the best performance for fraud detection using normalizing flows? And we were not able to find a universal best loss function. And instead of the choice, depending on a data set, like the best choice kind of depends on the data set. And the most important point over here is that with some objective other than using the base loss function, we were able to achieve better results across all different metrics. So how does the change of the loss function impact the final scoring? This one is showing the violin charts, and we're able to see how for PaySim and vehicle insurance, they showed more sensitivity. It showed more sensitivities to the loss function, and the real PCA. we can see that distributions of the violin charts, and for the pacing one, there's a very large distribution across different metrics that we were measuring. And for the real PCA one, where we had on the left side for the credit card ones, we see some differences between the performance of the different loss functions, but overall, it's not as large as the pacing one, which has large number of data points. And then, so the dataset performance is pretty diverse across different data. The loss functions performance is pretty diverse across different data points, and the synthetic data sets had for the pacing one, we were able to see a wide diversity in the outputs, but for credit card, which was a pre-PCA transformed and using actual data, that one had minimal diversity across of its numbers. So to conclude, loss functions effectiveness is dataset dependent. No single loss function wins universally. And ensemble methods are competitive and consistently on top ranking, but sometimes simpler functions like L2 and S spectral alone can match or beat them. And improvements often range from 3.4% to 7.6% per dataset for each of the F1 scores. And some of the limitations to address here is that we evaluated on the static data sets, not streaming data. So concept drift is not really addressed here, which is one of the most important problems with the financial fraud data. And our model did not necessarily outperform the state-of-the-art models that are out there for supervised methods and also some of the deep learning ones. But that was not our ultimate objective, and we try to aim to improve normalizing flows specifically for loss functions. And future.
Thanks, Amir. Your time is up. Thank you for presentation. Thank you so much. And do anybody have any questions to Amir, please? Okay. Thanks, Amir. Thank you so much, and we'll move on to the next one. Thank you.
Thank you.
The next paper is paper ID is 241, quantum safe countermeasure mitigating detector bounding attacks in quantum key distribution system, Whale Jita and Malik Malkawi.
Yes, can you hear me well?
Yes, 10 minutes is the presentation, and we'll open for the questions.
Okay. 1 minute because I need to open the.
Yeah, I'm able to see and I'm able to hear as well.
Okay, thank you so much. Okay.
Okay.
So, hello everyone. My name is ISDFS, and I am from the Department of Computer Engineering at Istanbul Medipol University. And today I will present the paper work that is titled Quantum Safe Countermeasures Mitigation and Detector Blinding Attacks in Quantum Key Distribution Systems. So basically, this research is just focusing on the improvement of the practical security of the quantum key distribution systems, especially and specifically we are addressing the hardware level vulnerabilities in single photons detectors. So as a motivation or from where I got the idea for this paper, basically the quantum key distribution, or we can say the QKD, provides methods for generating like a secret cryptography and keys based on the principles of quantum mechanics. But however, like in real world deployments, the practical hardware they are not perfect, and also can introduce vulnerabilities, many vulnerabilities in real world. And also one of the practical dangerous, we can say as example, there is a detector blinding attack, and in this attack specifically, we have like an adversely injection, like a strong optical power inside the channel, and also into the receiver's detector. detector. It's forcing them like to behave in classical way, and also allowing the attacker to manipulate measurements and also outcomes. And for the problem statements here, because most of the practical quantum key distribution systems are monitored security using the quantum bit error rate, or we can say the QBAR. And normally, when we have a detect of a high QBAR, it's automatically indicates that the presence of an attack or the noise. But however, the detector blinding attacks are like probabilimetrics because it makes a lot of problems during the process because they can be manipulated like as a detector behavior while we have like a error rate within the acceptable limits. And also this means that the system may be accepted a compromised key without detecting the attacks. Therefore, like reliance solely or alone as a detector and quantum bit error rate alone, it will be like monitoring as insufficient for detecting this type of hardware attacks. So from the all of that, we came for the idea of as the objective of this research, that's addressing this problem. Like we need to propose a receiver side hardware aware defense framework, and from this hardware aware defense framework, it must be like continuous monitoring the physical indicators. And also, it must be first of all make optical power levels reaching the detectors. After that, it must be given a statistical patterns for of detector clicks. And these two monitors mechanism are like correlated to detect abnormal behaviors. And also, the goal is like to identify the attacks early, and also abort compromised key generation session, and without any modification and underlining the quantum key distribution protocols. And for the main contribution for in this research, this work is like makes for the about main four main contribution. The first one it is about the development a simulation model of detector blinding attacks in practical quantum key distribution receiver. And secondly, we propose a hardware aware monitoring framework and making integration of a receiver side. And thirdly, we design like a dual detection strategy combining like optical power monitoring and also statistical click analysis. And finally, we evaluate all the system using a Monte Carlo simulation to measure detection performance. And for the proposed architecture that we use, like the proposed architecture is consists of three monitoring layers. The first one is the optical power monitoring, which detects abnormal illumination levels that may indicate a blinding attempts. The second one it is detector behavior monitoring that analyze the statistical patterns of detector clicks events. And the third, it is about decision layer, which correlates the alerts from the monitor models, and if there is any abnormal, it is detecting the system will abort the key generation session and to prevent like, any compromised key acceptance. And all this approach will follow the difference in depth, like a principle that's commonly used in cybersecurity systems. And for the detection method, detection mechanism are uses two complementary methods. The first one, the first method, we can say that optical anomaly detection. It is given RS is triggered like when the incoming optical power is exceeded, and also it give an indication that the detector may have entered an abnormal operation region. And also the second one, which is method used the statistical monitoring of detector clicks. We compute Z score based on the difference between the observed and the accepted click counts. If the like, for example, if the deviation is exceed the threshold, the system will flag a statistical anomaly. Together, these two like mechanism will enable and make a detection to both strong and subtle attacks. And for the simulation setups, for the simulation setup, to make an evaluation of the framework, we develop a simulation-based model of the quantum key distribution receiver. Each simulation session, it will be include the 250,000 pools, and to ensure like the statistical stability. And the key parameters are including like a click probability of 0.88, and also a power threshold of 0.555, and also statistical threshold of 3 standard deviation. And we tested the framework under the three scenarios: the normal operation, and also a detector blinded attacks, and also and finally the an attack with the proposed defense enabled. And for the experimental results, the results were evaluated using a Monte Carlo simulation across like multiple attack profiles and including steps attacks and ramp attacks and also opposite attacks. And the combined defense achieved like a true positive rate of 1, meaning that all attacks are detected and at the same time the false positive are remained at 0, meaning that no normalization were like incorrectly avoided. And as a key observation, like from our experiments, there are several important observations like emerging here. First of all, detector blinded attacks can bypass traditional quantum bit error rates monitoring, and second one, optical power monitoring like detects strong limitation attacks quickly, and thirdly, statistical click monitoring detects more stable changes in in detector behavior, and finally, like when both mechanisms are combined in one framework, it provides a robust detection with no false positive in our simulation. And as a conclusion, like detector blind attacks exploit the hardware imperfection in practical quantum key distribution system, and we propose like a receiver side that's make a hardware aware defense framework, and that like making combination between optical power monitoring with statistical click analysis. And the simulation results like show that this approach can detect attacks reliably and prevents compromised key acceptance and as an important step that the framework can be integrated into existing quantum key distribution system without modifying the underlying protocols. And thank you. If you have any question, feel free to ask.
Thank you're on time. And yeah, the question is, what is the environment you used and with this simulation? What is the data set you used?
Yes, for
For
the data set that I use here, I use simulated data that I took directly from the simulation. For example, I simulate 250 pods directly from generated code because here I use like Python codes for the simulation keys and Python codes that simulate and generate like give a simulation data. I use it, but like for example, the code is already tested on IEEE datasets like contain a quantum key distribution channel already. But I didn't use it in the research paper because it is already have a framework, different framework, and doesn't like give good results, not like the simulated data because until now I didn't find a good data set for this framework. But like as a simulated data, or if you make a data customized by yourself, yeah, you can get some results, so good results to observe and see like the difference between the traditional framework and this idea or this novel framework.
okay, yeah. With that, thank you. Uh, Anybody have any questions? Okay, yeah. Thank you so
Okay,
much.
thank you so
Thank you for
much.
your presentation. With that, I'm going to move into our next paper. Paper ID is 245, Token-Based Authentication System Failures in Cloud Environment, a case study of the Microsoft Storm 0558 incident, Hamza Benlod and Malik Malkavi.
Yes, I'm here. Just a second, I'm sharing my screen.
Okay. Yeah.
Okay, so hello everyone. I'm
Yes.
Hamza Bimilud, and I'll be presenting our paper along with Professor Malik Malkawi. Our paper is titled Token-Based Authentication System Failures in Cloud Environment and a case study of the Microsoft Storm 0558 incident. So nowadays, cloud services rely heavily on token-based authentication because it enables scalable and stateless access control. But this use for that introduces new security risks. Before starting with the case we're going to study, we can go with the background. So some definition for some terms. token-based authentication. So a token is issued after authentication. So after the user logs in into a system, this token is generated. So next time he can be directly redirected to the related account. So it's often implemented using JSON Web Tokens, and it contains user identity, permission, and expiration time. It's verified using cryptographic signature. So we're using a signing key to verify this token. A signing key is used to sign tokens, and it ensures authenticity and integrity. But if that key is stolen, attackers can forge valid token, and the system cannot distinguish them from legitimate ones, as the signing key, I mean, it's like says this token is a legitimate one. For consumer versus enterprise identity systems, it's an architecture used by Microsoft in Outlook systems. So the consumer is for personal accounts, and the enterprise one is for organizations and government accounts. So now we can go with our attack overview. So in 2023, a nation-state attacker, Storm 0558, targeted Microsoft's cloud email services, and it accessed Outlook and Exchange online accounts, and some of the victims were of the US government, which makes it more dangerous. So we can see here the attack chain. So all the attacks started with the attackers gaining access to an engineering environment inside Microsoft itself. So inside that environment, they found a crash dump, an old one, and this one contained a consumer signing key. So with that signing key, they used to forge tokens and sign them with that consumer signing key stolen from the crash dump. So that consumer signing key, they use it to sign a token and access unauthorized mailbox of enterprise accounts, which wasn't supposed to happen. So the major failures in that case here, that as I said, weak trust boundary and no proper separation between systems. So the system was separated between consumer and enterprise, but the token signed with the consumer signing key was accepted by the enterprise environment. And poor key management, as the signing key was publicly available for the attackers, which wasn't supposed to happen from the beginning. We have here limited token monitoring as well, because the attackers stayed for a whole month using these forged tokens without being detected from the system. And the delayed detection, as I said, the attack stayed for a whole month without being detected. So here, as I said, is just a table that illustrates the failures. So we have tokens signed with consumer keys were accepted, which is trust boundary violation, and the consumer signing key was able to sign enterprise services, which wasn't the goal of the system developed by Microsoft. Also, using these forged tokens, there was no like extra check for that token if it can be used or not. So it bypassed everything and took you directly to the account itself, and no alert triggered for weeks. So here we have the delayed detection. For that case, we did an academic literature review, and we focused on two papers that for us, it gives a solution for that kind of attacks. If it was presented there, this attack couldn't happen. So the first paper, titled Token-Based Authentication Monitoring System. So the system the authors propose introduces 25 detection rules. Some of them are IP address, user agent, token use patterns, and token issuance sources. The accuracy, they said it's 81.4%. And for us, we believe that if this system was implemented in Microsoft environment, it could identify anomalies related to token origin, issuer context, and abnormal usage pattern. Because this token used by the attackers was an unusual pattern, it was an unusual IP addresses, and it wasn't issued by the normal issuer of these tokens. And the second paper we focus on is single sign-on authentication with anonymous token and restricted covert channel. So the authors propose a protocol called Sonar. This protocol focuses on anonymous token protection, but it has an identification for malicious actors. So the author said, like inside each token, we can have a hidden bit that only the original system can set. So if, let's say, an attacker stole a signing key and signed a fake token with it, that hidden bit will say non-set. So the system, even if this token is signed, it will not be accepted because this hidden bit can detect malicious token usage, even if its cryptography valid. So if we're talking about mitigation strategies about this kind of attacks and recommended protection, we need to have strict separation between identity systems. As here, Microsoft had two, the consumer and enterprise systems. We need to have strict separation so none of these keys can be signed in other environments. And we can use also short-lived signing key. So if that key would die, for example, in 7 days, the attack couldn't long for a whole month. We need to have more token-aware security monitoring. We can have automation in that, or with the use of AI nowadays. The system could detect the unusual patterns of token usage, and we can use key rotation and zero trust validation. So even if that token is cryptography valid or the system can accept it, we can have more steps to check if it can be used right here or not. Here is the same what I said. We need to have strict cryptographic separation of identity systems, short-lived keys, token-aware logging, and anomaly detection, and zero trust validation of token. What was learned from that case is that cryptographic validity doesn't always mean security. So even if these tokens used were cryptographic valid, but it goes here an attack. Also, identity systems require continuous monitoring and strict separation because this kind of systems it has privacy of the user, so it need to have always monitoring and security. Key management is critical. So we saw here that if that signing key was exposed to an attacker, it can cause more danger in the future, and we can apply zero trust principles. So we can't trust always a signed token. In conclusion, that case we studied, it exposed the weaknesses in cloud identity systems in a big company like Microsoft, and token-based authentication requires strong key protection, continuous monitoring, and strict validation controls. And it makes us think about future systems must adopt defense in depth, so we can detect these kind of attacks before an attacker can do them. Here are our references, and thank you so much.
Thanks, Amjad. Thank you so much. Anybody have any question to Amza? Amza, it's a great presentation. Thank you so much. I don't have any questions.
Thank you.
Okay, thank you. Okay, with that, we will be moving into paper ID 257 and big data driven AI models for network anomaly detection and cyber threat forecasting. Amit Kumar Meshram and Vikrant Sikawar. This is 10 minutes for presentation. After that, open for questions. Thank you.
Yep, thank
Please
you.
share your screen. Yep.
Sorry, this is. Yep. Okay. So, hey, hello everyone. Good afternoon. So I will be presenting our research paper, Big Data Driven AI Model Network Anomaly Detection Cyber Threat. With me, I have got co-author Amit Kumar. So Amit, you want to say hi as well?
Hey guys.
Hi.
Yep.
Thank you, Amit.
Yep. Let's get into it now straight away. Okay, I'll go to the slide 2. Okay, so what it is, so here is the structure we are going to go on our presentation today. We will move through our abstract, introduction, brief literature review, research methodology. We will going to discuss our results, and finally we'll close with our conclusions and future work. I'll keep each session concise just to respect our time for 10 minutes. Okay, I'll move to the slide 3. So overall, if we see that rapid growth of big data driven network infrastructures combined with increasingly sophisticated cyber attacks has created an urgent demand for intelligent and reliable anomaly detection systems that go far beyond what traditional security tools and conventional machine learning can offer. So existing approaches simply cannot process large scale network traffic in real time, nor can they capture the complex temporal patterns that characterize evolving cyber threats, such as DDoS attacks, brute force intrusions, and botnet activities. Our proposed framework is evaluated on the CIDS 2017 dataset, a comprehensive, well-regarded benchmark containing both normal and malicious network traffic. Our deep learning model, it's a bidirectional. LSTM achieves a detection accuracy of 99.58%, significantly outperforming all the baseline models we tested. Okay, I'll go to the next slide. Slide 4. So, yeah. So if I talk about over here, so with rapid expansion of interconnected networks, cloud computing, and data-driven services, modern networks generate enormous volumes of heterogeneous traffic data spanning HTTP, HTTPS, FTP, SSH, and more. Big data technologies now enable us to collect and process this massive data, but the security challenge has grown in parallel. Detection of network anomaly plays a very crucial role in identifying suspicious activities such as intrusions, denial of service attacks, and data exfiltration by detecting deviations from normal traffic behavior. Although challenges are there remain due to dynamic network conditions and high false positive rates. Traditional rule-based intrusion detection systems and standard ML classifications fall in three critical ways. They cannot scale to the big data volumes that we are seeing now. They miss temporal dependencies, meaning they treat each packet or flow in isolation without understanding sequence of events, and they struggle to adapt as attackers evolve their tactics. Our research directly targets these gaps by introducing a framework processing large-scale traffic data. We have used CICDS to evaluate 2070 to use that, uses PCA for dimensional reduction to extract the most informative features, and deploy a BLSTM deep learning model that processes network sequences in both forward and backward direction, capturing the full temporal context of an attack. I'll move forward to the next slide to the literature review. So to situate our work, I'll not go through the whole, but overall, here's the snapshot of recent studies which are already being done in this space. I'm going to highlight some of them. If you go for Cooley et al. To 2025, propose an adaptive threat intelligence framework achieving 95.2% accuracy. Patel et al. 2025 used CNN-based model for cloud security, reaching 95% accuracy. Janpure 2025 applied zero trust architecture with random forest, and they also achieved 98.64%. And Mohati, I'll say they use visualization-driven ideas with 97.9% FN score. These are really very strong contributions, no doubt about it. A common gap, but if you'll see across this work, is the insufficient modeling of temporal dependencies in network traffic and the lack of real-time adaptability for large-scale data. So, because traffic, if you see, traffic is a time-dependent sequence, not an isolated point. So our BLSTM framework is specifically designed to fill this particular gap. I move to slide 6, where we will go deep dive into now the research and methodology. Our methodology follows a well-defined reproducible pipeline. Let me take through each step. We can see this diagram over here, which will, like, if you see step 1, a data set, we use the data set which contains comprehensive representation of both Bengen and attack traffic. The data sets covers attack types, including denial of service, DDoS, brute force, botnet, and web attack across protocols like HTTP, HTTPS, FTP, and SSH. The distribution is approximately 75% Bengen traffic and 12% DOS and DDoS traffic, reflecting realistic network conditions across. Pre-processing, if you go for the pre-processing, what we were doing was exactly raw network data is never clean. So that's the first step. We perform data merging across multiple capture files, handling missing values, and remove noisy records to ensure data integrity. After that, yes, it was normalization. We applied min max scaling, transforming all feature values into range 0, 1. This prevents feature with large numeric range from dominating the model learning process overall. Dimension T reduction, that's the next step into the process. We applied a principal component analysis to reduce the feature space by retaining only the most informative uncorrelated components. This is not only speeds up training, but also removes redundant features that confuse the model. Finally, then we'll go to the data splitting for training and testing. We went with the 80-20 split, 80% for training and 20% for testing side. Now comes the important classification model of BLSTM model. This is the core of our framework. Is a bidirectional long short memory network. Unlike a standard LSTM that only processes a sequence from past to future, a BLSTM also processes from future to past, capturing context from both directions. For network traffic, this means model understands not just what happened before an event, but also what happened after, making it far more powerful at detecting subtle attack sequences. Okay, we'll go over here. So finally, we were evaluating our model performance. Is evaluated matrix elements, TPTN, FPN, FN metrics such as accuracy, precision, and all, and ROC curve evaluation as well. I'll go to further to slide 8. Let's talk about results and discussions around those. So if you see, say this shows the whole confusion matrix of BLSTM model indicating very high accuracy and classifying normal and abnormality traffic with minimal errors. Figure 3 on right-hand side represents a stable training and validation accuracy across epochs. So we're capturing all these things we have done across in this particular data set. Going to slide number 9. So, if we also do the comparison, in fact, if I give the performance metrics for our BLSTM model, we can see that we are pretty much good on accuracy, 99.58, precision, 99.45, recall, 99.35 with F1 scores compared to other I'll say logistics regression or maybe autoencoder. So all these models, our BLSTM model clearly dominates across all 4 metrics, notably logistics regression. A popular baseline achieve 96.6 accuracy, but falls short in capturing the complex temporal patterns that our model handles with near perfect precision. Light GBM, I agree, despite being a powerful gradient boosting algorithm, achieves only 91.35 accuracy, demonstrating that tree-based methods are less suited for sequential temporal data compared to deep learning. Talking about the autoencoder at 88.28% shows that unsupervised reconstruction-based approaches, while useful for anomaly detection, lack the supervised discriminative power of our architecture. So overall, I would say our model's confusion matrix confirms minimal false positives and false negatives. That's important. The ROC curve shows near perfection area under the curve. That's accuracy and loss training curves confirm the model converged smoothly without overfitting, validating the effectiveness of our pre-processing and PCA pipeline. With that, I will just conclude and we'll go to the future work, slide 10. So to conclude, our research demonstrate the BLSTM model integrate with systematic pre-processing, minimum max normalization, and PCA-based future reduction provides a highly effective and scalable solution for network anomaly detection in big data environments. With 99.58 accuracy, 99.45 precision, 99.34 recall, the model significantly outperforms traditional and existing ML-based approaches. The bidirectional temporal learning capability is the key of the whole innovation part. It enables the model to understand full attack sequence rather than isolated events. For future work, we are targeting 3 directions. First, real-time and online learning capabilities. So the system can detect threats as they happen on live traffic. That's important. Second, incremental learning, allowing the model to continuously adapt to new and unseen attack patterns without full retraining. And third, I will put explainable AI, XAI integration to make model decisions transparent and interpretable for security analysts and compliance teams. With this, I think I'll go to final. These are all the references that the full reference list.
Yeah, fine, Vikrant. Yeah, fine. Thanks for presentation. Anybody have any questions? Okay. Question from Vikrant and Amit, right? How much how many samples or how much of records into 2017 data set having you
So
used?
2017 records, so this is a pretty old data set, right?
Correct.
Yeah, this is a pretty old data set.
2.8 million records.
It's a 2.8 million records?
Yeah.
Okay, how many samples and features?
I think
So-
it's 80. Go ahead, Vikrant.
I know, yeah, we have taken around sample of around 100K to 200K records that we have done overall.
Okay. Okay. So real time, if you go, how you are going to handle it in future, right? That's what I was my question.
Yeah, so basically we do have tested with our different systems. Actually, I'll say we have increased and checked the performance, how the system will behave on some of the data we have just taken, just sending the data across, and how whole computation of the cluster size and performance is working, about the memory and all those things, right? So we have taken that into our account already. So most probably we see once the system should scale up accordingly, and that transition should be fine, because though
Okay.
the sample was 100 to 200K records, I'll say, but overall we also did some sampling test with a huge data set.
Okay. Hey, thanks, Vikrant, and thank you, Amit. We'll move on to the next one. I think you are the author only, same. Please share that one. It's a
Yeah.
paper ID is 263. Artificial intelligence-based anti-money laundering solutions enhancing detection accuracy in high-volume financial data.
Yep, correct.
Okay. Yeah, please.
Just a second. So this is. Is my screen visible?
Yes.
Okay. So, yep. So yeah, good afternoon, everyone again. So this is this is another paper titled "Artificial Intelligence-Based Anti-Money Laundering." So we both, me and Amit, are both have part of this paper on the research side. I'll just move on the slide too quickly. And yeah, here's a quick roadmap, like it's a similar one. So we will go with the abstract, introduction, literature review, methodology, result analysis and discussion, conclusion and future work, and we'll talk about the differences. So I'll go to the slide 3 of abstract, actually. So yeah, so if money laundering has become increasingly difficult to detect, largely because of the explosive growth in digital banking and transaction volumes. Traditionally, rule-based AML systems were designed for a different era. They struggle to adapt to evolving laundering tactics, produce a large number of false positives, and simply don't scale well. So to address this, our study proposes an AI-based ML framework evaluated on 3 machine learning models: XGBoost, XtraTrees, and hybrid stacking enable, tested on well-known PaySIMs, synthetic financial data set. We also incorporate explainable AI XAI to ensure more model decisions are transparent and interpretable. Our best model achieves a direction accuracy of 98.03 and offering high computational efficiency for large-scale AML deployment. I'll go to slide 4 with the introduction. So money laundering globally accounts for estimate 2 to 5% of global GDP, roughly 800 billion to 2 trillion annually. That's a huge number, actually. It typically occurs in 3 stages: placement, introducing illicit funds into the financial systems, layering, disguising the trail through the complex transactions, and integration, reintroducing the now clean money into the economy. So it has serious social and economic impacts, and government across have implemented strict AML regulation requiring financial institutions to monitor and report suspicious activities. If I talk about traditional AML systems rely on static rules and thresholds, which are easily bypassed by sophisticated schemes. They also generate huge volume of false alerts that burden compliance teams. The shift to real-time digital payments has only made it this worse. This motivated us to explore how enable models can offer a more adaptive, scalable, and accurate solution. The proposed study presents an AI-based AML framework designed to detect suspicious financial transaction effectively and support law information enforcement agencies. I'll go to the slide 5, which will do the compare of literature review. So there are prior work in this space, explored various ML approaches. Studies have used random forests, SVMs, and neural networks for fraud detection with mixed results. Key challenges identified in literature include extreme class imbalance, fraud is rare, lack of real-world label data, and model interpretability. Our works build on these findings by combining internal methods with SMOT for imbalance handling and XAI for interpretability, addressing all three challenges together. Okay, so if I go to our methodology, so our methodology follows a structured pipeline. Let me walk through all the steps actually. So data set, we use a PSLIM, it's a synthetic data set which contains over 6.3 million financial transactions. We sampled around 200K transactions for our experiments, which is still high volume benchmark, I'll say, as per the things. For pre-processing, yeah, we perform in percentile-based outlier removal, specifically between the 0.5th and 99.5th percentile to eliminate extreme values, analyze features distributions to understand pattern, and detect anomalies before modeling. Category features like transaction type, originator name, and destination name were handled using label encoding. So we were defining the separate input and future X and Y separations for supervised learnings. Normalization, we applied standard scalar to normalize all features to a consistent scale. Class imbalance, this was a critical challenge, I'll put it this way. Of course, fraud accounts for only about 0.1% of transactions. We applied SMOT, which is synthetic minority oversampling technique, to synthetically generate minority class samples and balance the data set. Train test split, again, we were doing 80-20 split, 80% for training, 20% for testing. Models trained, I'll go overall. XGBoost we did. XGBoost we did extra trees. So we used actually pre-mutation features, importance for XAI to identify which features drive model predictions. Final performance outcomes and comparative analysis of models were finally being shared across. Go to results and analysis overall. Now let's look at the results. All three models were evaluated for accuracy, precision, recall, and F1 scores. And the hybrid stacking model delivered the best overall performance with balanced precision and recall, making it both sensitive to fraud and precise in its predictions. XGBoost was very close second and remarkably fast at only 5.83 seconds of training time, I'll put this way. Extra trees, while slightly lower in accuracy, is notable for its computational efficiency, making it strong candidate for resource constraint environments. I'll move to give more on the results actually. So we also conduct an abolition study where we removing depth control of extra trees. Accuracy jumped to 99.98%, which is a red flag for overfitting. Reducing the number of trees dropped performance to 99.59. So this confirms the importance of our chosen hyperparameter configurations. Okay. If we talk about for the comparison of traditional methods like logistic regression, which achieved 90.44 SVM achieved, that was poor actually, 33% only, and Tencent 121 reached 89.11. So our proposed AI models clearly are outperforming those things and are doing better. So our XAI analysis using permutation importance revealed that the three most influential features are new balance origin, new balance of originating account, name of destination account, and the old balance for originating account. This makes intuitive sense actually overall. Sudden large transfer draining an account or a hallmark of layering behavior. Overall, I'll conclude, and for the future work. So to conclude, our AI-based AML framework successfully addresses the core limitations of traditional rule-based systems. The hybrid staking enable achieve state-of-art performance at 98.03 accuracy while maintaining strong precision and recall balance. The inclusion of explainable AI ensures that models' decisions are not a black box, which is critical for a regulatory compliance in the financial sector. For future work, we plan to validate on real world financial data sets because that's very important. Integrate behavioral and network based features such as graph analytics to model transaction networks and implement adaptive learning mechanism to handle concept and drift, where laundering patterns evolve over time and the model must update accordingly. We believe this framework represents a meaningful step towards scalable, intelligent, and explainable AML systems. Thank you. That was
Vikrant, thank you so much. Thanks for your nice presentation. Great work. Anybody have any questions to Vikrant and Amit about his research? Vikrant, is it a extreme gradient boosting? Is it overall is a good model for your overall performance, or a hybrid model is?
No, hybrid is better actually, right? So that's what we are going with. Yeah, that's actually it's a fair point. Percentage terms, I'll say the gaps is very small, right? So, however, in volume financial setting, processing millions of transactions daily, even 0.3% improvement, I'll say will translate to good one, right? So,
Okay.
both are real compliance actually and financial cost. We have to look towards that actually overall. Yeah.
Awesome. Yeah, great work. Thank you so much. Thanks for presentation.
Okay. Thank you.
Yeah.
Thank you.
With that, we are moving to next one. It is a paper ID 317, performance analysis of a cloud native web application deployed on Kubernetes, Dharmendra Ahuja, and presentation it will be 10 minutes, and after that we'll have questions. Yeah.
Okay. Thank you, Shiva.
Hi, Dharmendra. Yeah,
Hi,
please share your screen. Thank you.
Thank you. Are you able to see my screen? Just to double check.
Yes.
Okay, perfect. Thank you. So I'm going to talk about the performance analysis of cloud native web applications, which is deployed on Kubernetes. So this paper is more about a comparative analysis of the performance between the static static application deployed on a cloud Kubernetes environment. So the idea is to compare the performance when we have an auto scaling and when we have auto scaling in place using a horizontal pod auto scaling. So we are using cloud native e-commerce recommendation application, which is deployed on EKS in a production like environment. So in this paper, like we are trying to analyze the performance by comparing both this static and auto scale deployment using, and we are measuring the matrices like a response time, latency, throughput, CPU utilization, and also like node hour consumption. And we will see in the results like like HPA, when we are using horizontal pod auto scaling, it doubles the throughput between 500 to 50 to 800 requests per second and reduces the peak response latency from 600 millisecond to around 110 during the high load scenarios. And also auto scaling like decreases CPU utilization from 90% to 65% and reduces overall node hour usage as well by 50%. And in this paper, like we are using Prometheus for performance collection, data collection, and for logs collection, and Grafana is for visualization we are using. And so I'll talk about like what is the background behind the cloud computing and the auto scaling these days. So like cloud computing is like has transformed a lot, where we are doing deployment from like traditional monolithic architecture to like a cloud native approaches. And there is a lot of emphasis on automation, like scalability and resilience. So containerization is very popular these days, and we are packaging application and dependencies into like containers and enabling consistent deployment across environments. And though managing large scale microservices manually becomes like very difficult without automation, so Kubernetes has come into a picture and for helping for containerized applications and providing like automated deployment, scaling, and load balancing, and fault tolerance, and also self-healing capability in distributed environments. And the work we've done as a case study for performing for evaluating the performance impact of using HPA on a cloud native environment. So the and also the in the study we are investigating like how HPA affects like throughput, latency, CPU utilization, and scalability under varying workload, and overall operational efficiency compared to like a static deployment. I'll go to the next slide. So as part of the research, like we have done like gone through like a lot of material already available, like the research already done. So there are several authors who have published a paper. So one of the author, like Noor, has published a paper in 25 where comparative analysis was done on ARM architecture in Kubernetes. And they have find like it shows potential improvements in scalability and cost efficiency and performance of the deployments. But there were some limitations, like they were like they had limited real world large scale validation, and they have a limited for future work they are focusing on broader workload diversity and long term cost benchmarking. Similarly, there was another paper considered like automated monitoring framework using Kubernetes, Prometheus, and Grafana. And so they had finding on like system efficiency improvement and optimized memory and management and CPU utilization. So they were focusing mainly on monitoring future work, which could integrate predictive auto scaling and anomaly based remediation and so on. So and like the past paper was also considered like for formal modeling of Kubernetes based cloud application using real time APS. So here we have enabled like a scalable simulation of large environments and resource modeling, and the model based evaluation was the limitation, and future work would validate simulation results against real production cluster. So now I'll go to the cloud native architecture. So cloud native applications are deployed within the like all the applications are packaged together. Application components are packaged together, and development refers to like designing and building application for like a cloud environments and leveraging distributed infrastructure, automation, scalability, and continuous delivery practices. And the modern cloud native system rely on technology like container orchestration platforms like Kubernetes and microservices architecture and serverless computing to enable like flexible deployment, resilience, and dynamic scalability under changing workloads. So, like microservices architecture is influenced by service-oriented architecture, and where we are structuring like application as small as possible, and they all talk to each other with using lightweight APIs, and so that we can do the modular development, and so that they can be easily scaled. And containerized applications, so in like what we do is like we try to package all the lightweight components together and portable containers, and making sure that they're consistent runtime environment across the development, so that we can do the development and testing in a like environment, so that we don't have a chances of failure. So like in the DevOps practices, we do the development and operations through the CI/CD pipelines, and so continuous monitoring and automation helps a lot. And we use tools like uh, Grafana and Prometheus for monitoring purposes. Um, so I'll go to the next one. Here in the orchestration platform, like it's like Kubernetes like a orchestration platform where we automate the deployment and scaling and management of like applications across cloud and on-premise environment. And in this orchestration platform, we have a master worker architecture where we have a control plane, and we will see in the diagram later on, where we have a control plane maintains that like a desired cluster state, and it schedule the workloads, and worker nodes like provide the compute and storage and networking resources to the application pods. And we have the term called pod, that is the smallest unit, and the pod can have multiple containers within that. And the control plane we have, which contains the edge set, which is like store the metadata. And also we have a API server, which is like a cluster communication interface to talk to APIs. And we have a scheduler, which is like a scheduler. The main job is to schedule the pods. And we have a controller manager, which does the state reconciliation. And if there is any node failures or anything, it will just try to get the nodes back to the ship. And like worker node will run essential components like a kubelet and a kube proxy for handling the networking load balancing. And we have a container runtime environment also like Docker, that which executes the application containers. So as part of the case study, what was done is like we created a cloud native e-commerce application. It was just like a dummy application we created, which is deployed on Kubernetes to deliver real-time personalized responses and with low latency and high availability. And then application had like three layers. It has a REST-based fast API layer, and it has also had a TensorFlow layer, uh, and also it has a Kubernetes horizontal pod scaler for dynamic scaling. And for real-time monitoring and performance visualization, we did using Prometheus for metric collection and Grafana dashboards for dashboard visualizations, so that we can do the analysis of the logs collected. And the experimental step, which is include like a synthetic workload generation up to like 100 requests per second. And so we had a with a stateless compute intensive. So what we saw that like with the help of HPA, we can scale the load from 1 to 4 pods with when the CPU utilization is 70% and above. And so performance is like evaluated using like the key parameters like throughput, request per second, and response latency, and CPU utilization percentage, and also assessment of like scalability and resource efficiency. So if we look at the results here, so when we had no auto scale in picture and when we have auto scale in picture, so we are just comparing the performance. So throughput was improved when we from no auto scale, it was 50 requests per second, but we were able to achieve 100 requests per second when we had a HPA in place. Similarly, latency was like very high. It was greater than 600 requests per second, and then we were able to achieve around 110. And CPU utilization was like close to 90% when we didn't have any auto scaling in place. But when auto scaling was enabled using HPA, we were able to achieve like 65% CPU utilization. And the pods were fixed, like one pod was there. But we were able to, when we did auto scaling, we were able to scale from 1 to 4. so so nodes hour per day were like 96 hours were there. And but when we had two nodes in place, then we were able to 48. So this is the improvements we are seeing when we had order scaling in place. So like I already discussed about the results. So the idea is like when we had auto scaling in place, it helps a lot with achieving auto scaling, CPU utilization, and memory and throughput. Right, throughput also increased, and application pod were dynamically scaling from 1 to 4 replicas without any issues. So the overall cost efficiency was also increased with the help of auto scaling in place, because node hours were reduced by 50%. So which shows like enhanced cost efficiency without compromising the performance. So if I talk about the conclusion, so as part of the study, uh, we found that like Kubernetes based container orchestration with HPA, it effectively manages the dynamic workloads in cloud native e-commerce applications. And auto scaling helps a lot. It improves the throughput and reduces the latency at peak by balancing CPU across the nodes. And dynamic scaling helps with the provisioning, so it reduces the over provisioning of the nodes, and it leads to like a 50% reduction in node hours, which helps a lot with saving cost. And so in future, I'm planning to focus on not just on a CPU utilization. I'm thinking about uh, work on memory aware and network aware auto scaling process, so that we can do some more research on that, and see how we can help the industry with those ideas. And also planning to do this kind of testing in ARM based nodes and multi-cluster nodes in Kubernetes environment. And also have another paper work going on which is related to AI driven predictive auto scaling, so how we can use AI to predict the workload and auto scale the nodes accordingly. So as to do this kind of study, I have taken references of so many research already done, and it is already published here. Yeah, over to you. And if you have any
Hey,
question.
thanks, Dharmendra. Thank you so much. Thanks for your presentation. Yeah, it's a great research. Do anybody have any questions to Dharmendra, please?
Yeah, sorry, I think I forgot to turn on my camera, so sorry about that.
Hey, thanks for presentation, Dharmendra. Thank you so much. Thanks for your time. And yeah, it's a great presentation.
Thank you. Sure.
Okay, yeah. With that, we'll move on to the next one. Paper ID is 363. Safe Kid Scan, Early Detection of Digital Addiction in Minors. Anjana H.
Yes,
Perakodi YP, Gimani
yes, sir.
JMKP. Okay, yeah, please.
Thank you, sir. Let's move my presentation. And our research topic is SafeKit scan detection of digital addiction in minors. I am Anjana. We represent in Sri Lanka Institute of Information Technology in Sri Lanka.
Okay.
And most Sri Lankan students aged between 10 and 18 getting their moms or dad phone, share social media account, they log in social media platform. After they doing many kind of activities, but it has a dark side. And I'm volunteering in Sri Lanka largest volunteering organization in a Hitavadi program. Most student addict the social media platform and social media content. It's a huge issue. And other very important thing is Sri Lankan parent does not have enough knowledge to identify the type of addictive child, and they don't know how to prevent those child. And other very important thing is earlier addictive content identification methods are very slow, manual, and they have different kind of security issues. In that case, we building a SafeKit scan. SafeKit scan has a different kind of advanced features. First one is multimodal AI. Second one is complaint-driven system, and third one is IoT integration, and final one is secure reportings. And multimodal AI means we use different kind of AIs and different kind of large language models and different kind of machine learning models you use to this analyzation parts. And complaint-driven addiction driven system is we use different kind of machine learning models for analyzing two different ways. First one is word analysis, second one is word phrases analyzing. It is very important for future. It is very important for getting the full idea of the single language. Single language means most Sri Lankan speaking mother tongue is Sinhala. And third one is IoT integration. IoT integration means we building a wearable IoT device. It is very helpful for doctors to immediate getting the medication parts. And final one is secure reporting. Secure reporting means that kind of system want to very secure parts, secure systems. In that case, we added in secure reporting parts. Let's move my next slide. This is a proposed system architecture. You can identify this system can use a minimal input. It is very important thing. The first one is image upload. First image upload mean we use addictive child, most of the social media content is screenshots. And second one is details. Details mean we use child details and child behavior details. It is enough to analyze in those contents. And Sri Lanka government support to build this system. In that case, we allocated some CCID and law body. CCID means Sri Lanka Criminal Police Department, and other one is medical health. Medical health means allocated some volunteer doctors and mental health doctors. These are secure database. Secure database, we save in all data, all reports, and all biometrical data secure in this database. And other one is secure chat box. Secure chat box mean users or parent want to get in the more help, more details, and they use the chat box and chat in those medical health and CCID and law bodies. It's very important part of that. And the important thing is things of that research. And first module is visual and media and sentimental analysis. And in that case, we use a first input. First input means most child most watching social media content screenshot. Let's go in that screenshot analyzing part. We using analyzing in a different kind of AIs and different kind of machine learning models and large language models. We analyze and posting patterns, image data, caption data, and hashtag data. Finally, we generate the resist scoring. This is our resist scoring algorithm. We especially thank you Sri Lanka Child Care Authority and Sri Lanka Dangerous Data Board for support this algorithm built. And second one is comprehensive and intelligent. Comprehensive and intelligent means we use the second input. Second input means child data and child behavioral data. Child behavioral data can upload two different ways. First one is voice submission, and second one text-based submission. It is very important for disabled people to handle this system. All data is going to analyzing part. Analyzing part, we are analyzing behavioral patterns and the resist scoring and other many important data we analyzing. Finally, we generate the report card. Report card means analyze, include all the details and behavioral patterns and other data. We include the report card. That report card is stored in our secure database. And third module is IoT and physiological monitoring. And first two modules analyzing system suggests for that child want to immediate medical actions. In that case, system allocate the doctor and system automatically allocate the sessions and free of charge. And in that case, doctor can use that wearable IoT device. That device includes different kind of sensors, and first one is heart sensors, body temperature sensors, motion sensors, voice analysis sensors, and different kind of sensors include that device. And all sensors data, let's go and analyzing and getting some suggestions for doctors. It is very important for immediately get the medications. And finally, we generate the digital health card. It is very important and first time in developing Sri Lanka. And it is very important for future medications. And final and very important layer is trust layer. Trust layer means all reports and all data redirect this trust layer, and trust layer analyze all report again. It is very important for that type of systems, and analyze those reports and generate final reports, and using some algorithms for secure those reports. And in that case, some others want to change those data, but our report can't change anyone because we facilitate to and facilitate for validate the final report. This is very important for future legal actions. And this is our experimental validation accuracies. It's a media analysis accuracy, complaint analysis accuracy, and IoT module final accuracies. And this is performance discussion and impacts. We use a multimodal AI, which is very important for deeply analyzing. And second one is earlier system very slow and manual and different kind of security issues. Then our system very fully automated and fast analyzing and guide for parent and users for every stage how they want to do, and all things are guidance. And this is another very important thing, privacy, ethics, and governance. Our system fully automated, no any human involvement in that system. This is very important for data leakage issues and other privacy issues. And other thing is final report can validate for in our systems. And this another thing is anonymization and guardian supervision is important for privacy parts. And these are final things of my presentation and conclusion and future horizons. This scale, we can scale up this system using the vision LLM models and other different kind of advanced model, and we can use the multilingual support, added some different kind of other languages, and we can add some advanced sensors for wearable devices and different kind of things can do in the future. And thank you, sir.
Oh, thank you so much. Thank you. Thanks for your presentation. Anybody have any questions to Anjana? Okay, thank you, Anjana. With that, we concluded all our papers, and session 5 presentation, all the papers is completed. Thanks for everyone. Thank you so much. Thank you for your cooperation. With that, I'm concluding this session. Thank you. Great works.
Thank you.
Thank you.
Thank you, sir.
Thank you.
Thank you very much. Thank you for your session chairs, and thank you for all presenters.
Thank you. Yep.
Thank you.
And about 15 minutes later, in-person presentations will be started in this room. You can stay and you can listen to in-person presentations in this session.
Okay. It is here. Sorry. And we can do well. It's okay. Just find something to see if and it means
the system stored, no traces were in fact left. Can be gathered in these circumstances. To begin the methodology, I'll first go over the environmental setup. On a Windows 11 laptop, we set up a virtual machine using VMware Workstation that was executed as live and non-persistent. This virtual machine had a Tails operating system with no persistent storage enabled. We also had a SanDisk portable SSD. Using this configuration, we were able to perform a series of 8 experiments designed to leave common artifacts of user activity. First, we opened and closed KeePassXC, which is Tails' pre-installed password manager. Next, we configured an email address into Thunderbird, which is Tails' pre-installed email client. Next, we opened and closed Metadata Cleaner, which is a program in Tails used to remove metadata from files. And then we visited multiple websites on the Tor browser, from which we downloaded some Java files and some MP3 files. With one of the Java files, we wrote to it and saved it. We also created directories and spreadsheets as well. We deleted one of the directories to see if we could retrace it later. And lastly, we mounted an SSD. After this series of experiments, we created a RAM capture with FTK Imager before shutdown. We used the Volatility 3 commands to identify the VMware executable process, which was at process ID 12432. And from this process, we derived a memory map to help filter out host noise from the Windows system. With the help of generative intelligence, we implemented a bash script to search through the RAM capture and the memory map for a predefined set of keywords. This script organized these search results by encoding and keyword into separate text files. This is the command we use to see the processes contained in the RAM capture. The highlighted element is the VMware executable. This is the command we use to create the memory map. I won't explain the full script here, but I do want to point out some of the most important keywords. Most importantly, we have the websites that we visited, including thefieryred.com and samplelib.com, in addition to names of the files that we downloaded, like sunshineyellow.java and sample3.java. In addition, we have the serial number of the SSD down in the hardware and identifiers section. By running this script on the RAM capture and the memory map, we got 2 folders of results. In each folder, there is a folder for ASCII results and a folder for UTF-16 results. And in each of those folders, there are 37 text files where the results for that keyword were compiled. In total, we had 148 text files. To go over key findings, I will first begin an overview of our artifacts. The keyword search returned artifacts spanning a large range of identifiers regarding 4 categories. hardware device enumeration, file system artifacts, network anonymity and session reconstruction, and software execution and usage traces. We did not recover every single keyword, including fiery red 147, which is what we searched in Tor browser. The RAM capture results were equal to or more numerous than memory map results for most keywords. This suggests that the memory map successfully filtered out noise from the Windows host system. However, we still retain the RAM capture because it would allow us to derive insights from the virtualization configuration, which there's no better example of than for hardware enumeration. Inside of the RAM capture exclusively, we recovered string artifacts that are structurally consistent with Windows device instance IDs. Like the name implies, a device instance ID is composed of a device ID and a corresponding instance ID. In this context, the instance ID segment represented a stable local identifier that persists across restarts. The original serial number was not found anywhere as plaintext, and no local identifiers attributed to tails were identified. This suggests that the Windows host system compromised tails amnesic capacities by creating a persistent local identifier. The large string at the top is the UTF string that we recovered from the RAM capture. If we remove the bolded portion, we're left with a device instance ID, from which we can derive the device ID, which contains vendor, product, and revision codes consistent with device IDs for USB mass storage devices. In addition, we were also able to isolate the instance ID as well. Instance IDs can incorporate a unique identifier provided by the device's bus or enumerator. If the device provides its serial number, it can be potentially passed as a unique identifier. If a unique identifier is not provided, Plug and Play Manager generates a local identifier unique in the system. In this case, the instance ID does not match the serial number. This suggests that this is a local identifier constructed by Windows. But regardless of the source of origin, it is persistent across restarts. For file system artifacts, our search logic recovered file and directory artifacts. This included bookmark artifacts containing timestamps for added, modified, and visited. We even recovered a bookmark artifact for the directory that we deleted called blockbox. And we also recovered contents of a Java file as well. In this listing, you can see one of the bookmark artifacts that we recovered. Each of these fields, added, modified, and visited, have a timestamp associated with associated with 10-27-2025. And additionally, we were able to recover the print statement that we saved inside of the Java file as well. Search logic also recovered artifacts exposing elements of online activity, like the destination domains and file downloads. We recovered SOX artifacts that enumerated websites that we visited during the experiments with timestamps. We also recovered a plain text log of our download of sample3.java in experiment 5. However, we were not able to recover the email address or the password that we configured in Thunderbird. In this listing, we can see the timestamp and the enumerated website. And this is the log of our Java file download. We also recovered software execution artifacts that indicate that application activity persists as system logs. We found an AppArmor audit log that captured Thunderbird being denied access to a system file. We also found dbus logs revealing systemd service activation triggered by metadata cleaner, which is one of the softwares that we executed. To begin with the implications of this study, I will go over the takeaways and limitations. Virtualization and live memory acquisition circumvent Tails threat model and amnesic design. These circumstances, which specifically are pre-shutdown timing and configuration, introduce new weak points that can change forensic outcomes. This study does not seek to disprove Tails' privacy guarantees. However, it does seek to contextualize outcomes when traditional deployment assumptions are broken. In the future, we are planning a journal extension by classifying artifacts to memory regions and correlating artifacts. Thank you. Do you have any?
So go back to that email part. So when you said you did not find any traces of email when you were using Thunderbird, did you have like some encryption there? Like, did you set up an email with that public-private key?
Not that I know of when we were performing this experiment. The email address and password may be present, but it may be encrypted.
Yeah, that's what I was wondering. Like, since it encrypts a lot of things, and so that's the reason.
We suspected that as well, but we did not make a formal interpretation of that.
Okay.
I do also believe it was likely encrypted somewhere in the system as well.
And the other question regarding that metadata cleaner. So did you use like a software like CCleaner to scrub the things and get the traces from there?
We did not actually use metadata cleaner to scrub metadata from a file. Dr. Sinal just opened the application and then closed it immediately.
Okay. Okay, that's about it from my side.
Any other questions?
Yeah, one question.
Jaden, you said that you are freshman first year of San Jose.
Yes.
Yeah, how did you get into this as a first year? That's very impressive.
So one of my relatives once said in a passing remark, "Oh, San Jose State is doing research now." And that stood out to me because at the time I was deciding between San Jose State and community college.
Yeah.
The opportunity to pursue research is actually what led me to attend San Jose State. And I applied for their UROC program, which is their undergraduate research opportunity program. The director of that program takes this job very seriously and gives us a lot of support in matching with faculty mentors. I ended up matching with Dr. Nuretin Sinal. He ended up snatching me before I could interview another faculty that I was going to. But I am happy with the results, even though I would have preferred to have someone with a doctorate standing with me for this presentation. I am happy to be here, and I'll remember this forever, pretty much.
Well done.
Thank you so much.
For you. Okay. Thank you. Okay, up next is paper ID 372. So, okay, so it talks about governance and auditability of AI-driven retail decision pipeline and cloud-native architecture. So, Prithvi, the stage is all yours. Thank you.
So, the retail industry, we have a lot of things, right? Like we have so I'm Prithviraj. I work for retail industry for the last 20 years in different corporates. So currently with AI, we are trying to get most of the changes comes into automated, like let it be a price, assortment, or the point of sales audit. Everything has to be, or AI would help us. So okay, so the base is for any product to sell in retail industry, we have a cost to the company. Retail is what the company charges to the customer. So the cost should be less and the retail should be more. So far it is all manual. So we have the merchant planners coming and setting the retail or the assortment based on the different markets. How do they want to set it out? So when we started with AI, So we didn't have the governance, or we didn't start anything like. So we had our data, the raw data that started processing and try to fix the retail. So the retail, to give you a picture, right? Retail will be changing like few, at least few million times a day for a big corporation. So few million days you will be changing the price, and that's all manual. The merchant panel will come to it, or the assortment. Assortment will not be millions, but at least few 100,000 assortment changes will be happening. So to start with, we just want to say, like, I just want to start with what is the problem statement, and we'll go with what we have in the AI, what is the issues we have. So the current AI changes, what we did is like we started with actually we started with pricing, but lot of inventory supply chain everywhere we started using this. The black box AI model is a problem. Like just with the raw data of the past few decades, we just give the data, try to model it. So how does the retail changes? Retail changes with different season. Let it be a spring break, Thanksgiving, Christmas holidays. It will go ups and downs actually. And on top of that, we have our regulations, different regulations. Let it be California has its own regulation. Other regulations are there, which has to be followed over the nation. Okay, so if you look at the traditional is like manual checklist, right? You go back, look at it, tick on this, make sure that say for instance you have something like there are some advertisements. You cannot advertise, but advertise it saying like a new lower price. Blast it like for the same product again and again. You cannot do that. You have a 2 weeks time within which you have to do. So those things has to come under governance. And if it is there, the consumer can come back and sue it. So those governance has to be there. So on top of that, we deploy our instances, our code into a cloud. The cloud gives you the security and other things, but not with the tracing. What do I mean by that? Right? We have hundreds of instances running out. Say like in a Kubernetes or whatever engine, right? Like a compute engine. Few hundred instances for each thing. Whether it be pricing, let it be inventory, everything would run. You will not have a traceability where the decision has been made and what has been done for that. So we lose our traceability of that part. So we want to get into so what we want to do is we want to get into a framework which gives you you feed on the raw data, you get the raw data, you make the decision, the policies are enforced, say it will be a NLP, whatever it is, it has to be enforced, and then collect the audit and monitor the loss. So audit is like in a big corporate, there will be external auditors coming in, like the KPMG or whoever comes out. They need that audit trace for, it would be a random audit, but still you will have you should be able to prove to them saying that this is how the retail was changed, over this change, and make sure that all the policies will be adhered. So that used to be a manual. Now we have tried with this thing, we are trying to get it as an automated. So you can pull anything and you should be able to go back and trace it. So here what we have is we have our retail data sources. On top of the retail data sources, you have the AI decision pipeline, which feeds on the data. Then the price assortment is being ingested, processed. In meantime, we have the audit collector. The audit collector is actually not at that we just audit collector is like the interceptor pattern. At every point of time, it will try to get that information. It will collect that information, and we have that the business rules as code engine, right? Like rule engines, right? We have different engines like NLP or different on the assortment side. You cannot take a product in and out immediately in a store. On top of that, you have the audit monitoring. Say like a price change of a drastic price change. From say like a refrigerator being sold at $1,500 that been reduced to $500. That cannot happen. So that is where the monitoring comes in. It says like, okay, this is where your price for this refrigerator is getting changed. It's a drastic change. So make it prevention. Okay. Audit collector, yeah, that's what they explain, right? Like, so it has that interceptor pattern, and every time it will collect all the information, saying like before the approval, everything it will collect the points saying like this is the retail or this is the cost that has been processed, and it has not been changed for that SKU item. And generalized audit stores. Generalized audit store is to have everything like let it be a POS or a retail being sent through it, right? You collect everything, so we know from trace to okay, this SKU sold at this store, this retail, and this much of transaction has been made on that. And when it started, what was the inventory? So you have the whole trace of it, saying for every half a year you can go back and trace it out for this SKU. When was the retail change? How much orders was done, and what is it? And you can go back trace it out on different retails, so at different places. So whenever I say point of sale, that could be multiple point of sale, like the .com store. Store itself, you have different application where you can place an order and ship it out. It's not you don't pay it until you come back and take it. So it's different systems. You have to have the details. Monitoring and analysis. The policy as code engine is where we have the governance policies. All say like the NLP or a map minimum advertisement price. You have to have few prices. You cannot go down on that. So those kind of policies we have around them. If you take for pricing alone, we have around 1,400 to 1,500 rules has to be followed. That goes with different things like label printing. You have different rules. Those are all being put into a different rule engine. On top of that, the monitoring analysis will go on. Like if you have a different retail change, anything happens, a drastic change, that would be a letter. Okay, so for this, what we did is first we had a lot of accuracy issues when we started on the AI with the black box. We were not able to get it because it had a lot of changes that has less accuracy. So we took 491 instances. So the instances looks like, as I was explaining, it could be the flash sale or the April spring break, spring sales, or the Thanksgiving sales. We took the data, run out with scenarios because during that time, the retail is little bit or changes actually. It will be more during the time. So the cost to retail difference is different. It's more during that time. So we went with different scenarios there, got it out, cleaned up the data because sometimes, what do I mean by cleaning the data? The same data would be again and again be propagated from the start to the end, just for single. So those things would give a idea to the model saying like the retail is changing frequently, but it was not actually. So data cleaning and making sure what necessary data is done. And we have got everything in a Kubernetes environment. So that way the pods can scale up and scale down easily. So if you look at that after the mass data, the efficiency, the accuracy has improved. Actually, it has improved from 65 to 85%. This blue and dark blues, like blue is pre NPM and dark blues after NPM, post NPM. So the accuracy has improved a lot. I'll go back and show you the different systems actually. So these are the different groups have been taken out. So the pricing of different groups have been taken out, and we are looking at the accuracy. As the accuracy has changed for the cost or retail or the assortment side. One particular instant along the groups here on the assortment alone has little bit of accuracy still, but it's better than what it used to be. What do I mean is like the assortment has a inventory issues actually. It tied back to a different inventory issues. But other than that, if you look at the accuracy has gone up, the audit was success, and the latency has little bit increased few milliseconds. On an average of 14 milliseconds is what we were able to see an increase on it. But other than that, that is the all increase of latency we see. The CPU usage has gone down because the pods has been scaled down depending upon the usage. If there's no usage on it, we have got it down. So the gateway, if you see the gateway, that is at 8 percentage, and model core, that's the core where the AI decisioning is there. That is on a 45% of usage. So memory is related to that actually. So the machine type actually changed. Yeah. So end of the day, it is. So it has been recording only thing is like 14 milliseconds of time has been latency has been increased, which is not big of a time compared to the accuracy issues, the audit issues what we had. So we have started putting a blockchain for tracking it out. It's not completely, the blockchain has not been added for all the places. So which the blockchain helps us to go back trace it for each individual thing till the initial value. So that is where mostly we are trying to expand for the future. The blockchain audit storage, so that for all sales and everything we can go back. And getting the IoT of data system. The IoT of data system is for labeling and everything. You can on a real time you can push the data. Say the price, let it be a price or anything. You can on a real time you can do it all. And other things are simple things are add-ons for getting it with the federal integrating with the federal governments. These are all the data set and tools used, the regulation what we had. Kubernetes and Docker is what we install. That lives in Google Cloud Platform, so GCP. It's pretty much it.
Any questions for Prithvi?
I have a question on the latency. How can you get 100% compared, because in the computer time one latency that much and an accuracy that high is I can
If you think about latency, right, like when we say pricing, right, or an API, right, it goes around. We are around 90.
The time now is nanosecond, and then you on millisecond.
Yeah.
And you said accuracy. Oh God.
The accuracy is important because if you have a price change, right, yeah, it is very costly. It is very costly if you have a price issue, right, or for sort of assortment, it's going to be very costly. With 14 milliseconds is think about a price change from merchant planner to your store or .com, right? So your store or .com. 14 milliseconds is not that bad. When you're doing it manually, it used to be like 15 to 30 milliseconds approximately. As soon as the merchant planner puts a price to the end, it goes to 30 milliseconds, and you will not have an audit log or audit trace properly. This is 14 milliseconds adding to a price change to a system. At least on our system doesn't increase that much.
So where do you get the buffer for the cache? So for example, you capture the data. So you must have a buffer, right? So for example, you compare output to output, and you got this one. I just have this data 40 milliseconds later, and said I compared it.
So that's what the initial saying, right? Like it is on the manual. First was the manual, the second was the black box AI, where you don't have an audit. Okay, but it was faster because it makes a decision, pushes the data to the store or the pricing systems actually. So that used to take 4 minutes or 3 minutes. This would add few more milliseconds to it because of adding the audit trace. For audit collection, we are putting an interceptor at every point. So that adds the latency with 14 milliseconds.
But how can you come up with 100% accuracy?
100% accuracy is compared to the policy deviations we had in the initial thing, right? So say for pricing, we have around 1,400 to 500 policy decisions has to be followed. What does it mean is like you cannot breach a product by selling it to different retail or posting it as a sale. Okay, so that is a policy, and you cannot breach that by advertising it. So for simpler reason, I'm saying it as retail as one value. If you go back and look at it, you have multiple attributes to a reader. And there are different policies, government level policies on that you cannot go ahead and breach it. You cannot say like one day you cannot sell it at $5 and next day you put it as $3 and say like it's a great sale. There has to be a percentage of change and those policies has to be followed. If that policy is not followed, then we are breaching the accuracy. That is a violation of the government policy. So that is why we are saying 100% accuracy is on the policy calculations. Makes sense? No. Thank you.
Okay, up next is paper ID 395 from binary vulnerability detection to CV classification and hierarchical content study. Sorry. Yeah, press F5 probably and then.
Okay. Hi everyone, my name is Obina. I'm representing our title from binary vulnerability detection to CWE classification. So this study comes from the Department of Computer Science with GSU, and I'll be presenting on behalf of my co-authors. So what we're trying to do, we're trying to see if we can push AI to AI for detection, vulnerability detection, to see if we can push it like into detecting not just like vulnerability in code, and also like if we can see if AI can also tell us the main cause of the vulnerability. So, but before we go into the AI, before the AI thing, so let's first of all understand our target. So our target is CWE. So CWE is a community developed list of common software and hardware weaknesses. Types that will have security ramification, and also a weakness is a condition in the software, firmware, hardware, or service component that, under certain circumstances, could contribute to introduction of vulnerabilities, weakness, conditional, in many cases, introduced by developers during like development stage. So the problem is current AI2 or AI study only focuses, or like the model only attributes if a code is safe or vulnerable. It does not provide insight into the main cause of the vulnerability, and also it does not help developers or like guide them into targeted remediation. And at the same time, the most existing LLM work stays binary level, like if code is vulnerable or if code is safe. So, but we try to use fine-grained CWE classification. So we try to use CWE fine-grained classification. So we try to use this because it has 145 distinct CWE categories in evaluation. It also helps like identify exact vulnerability root cause, and also it enables systematic and also targeted fixes. And at the same time, it supports CVE, which is common vulnerability exposure, to CWE common weakness exposure enumeration, root cause mapping. So these are like examples of the CWE, CWE 120, 121, 125 buffer overflow, and a bandwidth. And so why exact CWE? Why exact CWE mapping matters? According to Mattia, accurate CVE to CWE mapping is critical for identifying the underlying root cause of vulnerabilities, and it enables systematic mitigations strategy rather than general fixes. So it helps with the root cause analysis instead of binary detection, because binary detection only flags code as vulnerable or like dangerous. But with CWE levels, it helps reduce why the code is vulnerable or why it is dangerous. So the exact class or flaws enabling the exploitation. So at the same time, it helps with the targeted remediation. So developers can apply CWE specific fixes, like bound checking for CWE 120 rather than general or generic patch that may miss the main issue. And also systematic security improvements where organizations can also as well track and prioritize CWE trends across all their code bases. And also enabling long-term vulnerability reduction rather than reactive patching. So we designed, from a methodology, we designed a pipeline we call hierarchical prompt refinement. So for the pipeline, we use a data set that has C++ code snippet functions. So we prompt the LLM to detect if the code is vulnerable or safe. Then for the first prompt, the P prompt, it's just basic instruction. It's just minimal instruction. There's no code, tax only, low CWE contents, just baseline. And for the second prompt, which is A1, it's hierarchy aware. So we use multi-CWE taxonomy. We injected that into the prompting, like when prompting LLM. So because multi-CWE has candidate CWE set and definition of this CWE and how they are linked, like parent, child, and siblings. And also, it's also best for exact CWE accuracy. And for the A2 is just like a context. So we just gave LLM sample of bug code, just like in context, like this is a bug code, like, use it to like identify if the code is vulnerable or not. So that's A2. So this is, and then it will attribute, it will assign, if it detects a bug, it will assign the vulnerable code ID, the exact ID, if it's ID, so CW 120 or 125. So for our experimental setup, we use SecEval datasets, and the SecEval dataset is more recent dataset compared to like older datasets because SecEval has 25,000 plus C++ functions, and also it extracted from vulnerable fixing commits. It also has a branch root CWE annotation, 145 CWE categories represented, and also it's rich when it comes to CVE mapping and context. And also it has paired vulnerable and also patched code. And for the model, we use GPT-4o, and we set the temperature to 0.3, and the max token is 256, and we did not include fine-tuning. We didn't do any fine-tuning, and also no RAG retriever was used. And the output format is CWE, like the ID, or if the code is vulnerable, say. And also we experimented this on two settings. So the first setting is the balanced data set where we use only 11 CWE from 119 family. And we tapped the data sets. We just made sure that all the samples are equal, so are uniform. And for the expanded data set, we use the same 11 CWE data, samples. Then we included cross-family. The cross-family is outside CWE 119, just to make it more realistic. So because the expanded data set has a natural long tail where it is not like clean, it's just distributed just not organized like the balanced data set. So for the key metrics, we introduced a new key metric called family accuracy. So what's family accuracy? It's a prediction is family correct if the predicted CWE falls within the same structural family as the ground truth. So sharing the same parent, child, or sibling relationship in the matter hierarchy. So so we also use the exact hit accuracy where predicted CWE is the ground truth for the detected CWE. And also near miss family, where the AI maybe detects the wrong CWE ID and also predicts the detected code as part of the 119, but at the same time it's wrong. So, and we also included like the cross-family error, where it is also wrong when it comes to like detecting the entire family. And for the sibling confusion, so this is the CWE 119 parent memory, and this is the CWE 120 the child. So they have similar code. They look alike, so it's very difficult for LLM to distinguish between these CWEs because they're like siblings. So when we run this test, we noticed that for the P, the binary, the P performed better when it comes to binary detection if the code is vulnerable or not. But for other like for the other exact CWE accuracy and family accuracy, whereas the A1, where we injected the hierarchy aware, performed best for the detection of the exact CWE accuracy and at the same time also the family accuracy. And for the A2, performed bad because the AI got confused because of we just gave it sample of the code, so it was difficult for the A2 prompt to help the AI to detect if a code is vulnerable or not, or like the real body code. So the analysis, so for the core observation, LLM reliably identified CWE family but frequently confused when it comes to siblings sharing the same parents. So when we use the balanced data set, the exact CWE, the results were really poor. And for the family accuracy, it stays at 0.56 to 0.67. And for the family accuracy, for the balanced data set, it was really high, almost like 25 times higher than the exact accuracy. And also, errors land in the correct family, not across the family. And why the sibling gets confused is because sibling shares similar code pattern. Like I said, it's very difficult for LLM to distinguish between the siblings when two CWEs have similar code patterns. And example like CWE 120 versus CWE 121, both involves buffer copy. So they also find range differences requires deep semantic analysis. And for the CWE levels from CVE can be coarse and sometimes noisy. And the impact of the class imbalance, siblings function increase under natural distribution, and the expanded data sets, more cross-family overlaps. So when we look at the A2 few shots, it drops to family accuracy of 0.318 and then in expanded data set. Then A1, most stable under realistic imbalance. So why hierarchy-aware prompting performed the normal, the basic instruction, which is the P and the A2. So the structural CWE knowledge injected the candidate CWE sets, one-line definition, and parent-child relationship gives the model the vocabulary and the context needed to reason at the right granularity. And at the same time, it helps to reduce search space by naming the relevant CWE family. And A1 prevents the model from guessing from 145 plus categories. And also, it effectively narrows the decision to correct structural neighborhood. And it also outperforms few shots under imbalance because few shots, A2 example, can introduce bias under natural class distribution. And A1 structural knowledge is distribution agnostic, making it more robust. So the binary CWE gap is real and significant. So the best binary F1 of 0.367 far exceeds best exact CWE accuracy of 182. And the prompt only cannot direct transfer binary detection skills to like fine-grained CWE classification without structural guidance of like MITRE taxonomy tree. And also the family accuracy is pure evaluation matrix because standard exact match accuracy misleads. Family accuracy also reveals that the most classification error are near misses within the correct CWE family. And it's not just random cross-family error because LLM gets the family right. Also, the hierarchy-aware prompting A1 is the most practical approach because injecting the structural CWE knowledge via A1 prompts performs both plain and few-shot strategy for CWE accuracy under realistic class imbalance without any fine-tuning. Thank you.
Thank you. Any questions, Robina? Thank you then. And that's just for you, Paul. Thank you. Thank you. Thank you. Okay, everyone, I think I'm the last in the presentation as well. So I'll be talking about enhancing phishing URL detection with machine learning algorithm. This is the research written by one of my students back in Wentworth Institute of Technology, Raymond Eichner. I'll try my best to answer the question and present his findings as well. So I'll try to make it a little interactive as well because I know it's a long day for you, everyone, and everyone is tired. So I really want to make it interactive session. Okay, so moving on. So these are the contents. So we'll start with motivation. We'll start to discuss about method, research, and logistic regression, and for classification, data sets, and followed by the results at the last. Okay, so regarding this phishing, so how many of you have seen phishing websites? And probably clicked on it to become rich, probably, right? Like 10 million bucks that you're getting, and that's about it, right? Okay, yeah. So this is always on the rise, especially in URLs and websites, always on the rise because everyone wants to get rich in some way or the other. And then since it's this contents of this website or the number of websites like this are quite increasing, manual processing is quite difficult. Right, I'm pretty sure if you check for all the website manually, it will make your life like a nightmare, right? So we need some automation tasks, like with the help of a machine learning algorithm and all the model, whichever you fit. Then, which once you have that, then your accuracy and efficiency becomes much higher. Okay, so that's the motivation behind this research. Okay, so again, we have like a lot of existing or a lot of detection models with something called list-based detection, with something called rule-based detection, visual similarity detection, machine learning detection as well. List-based detection, it maintains like a blacklist or a whitelist of a known phishing website. So how many of you can at least tell me what's a blacklist and a whitelist? Guys, help me out, please.
The blacklist is blacklisted, which is cannot be used. Whitelist is the list of things that you can.
Yes, yeah, did you add something?
I think that was a better explanation of what I was thinking.
Yeah, the black is all like no go area, white is all you can go to those areas and so on and so forth. Then there's something called rule-based detection. So like a set of predefined rules that we have to follow. Based on that, you're going to make a decision, of course. And there is something called visual similarity based detection. So this is more like a visual appearance of a website with no legitimate website. Okay, and lastly, again, with automation, so we have something called machine learning based detection. So once we have that, our automation will kick into our start doing this work. Okay, so again, this machine learning concepts, again, we have to have like a large data set. The more data set, the bigger data set we have, we probably will be having a better amount of training and testing accordingly. So like, for example, in our research or my students research, he did like 90% training and 10% testing and so on and so forth. Again, so this large data set that we have used, it came from like a legitimate website and like a collection of all the websites and whatnot. And they have classified like what's a good website and what's a phishing website. Based on that, our training model will try to figure out the efficiency accordingly. Yes. So like various models were used like logistic regression, support vector machine, random forest, like XGBoost, and so on and so forth. So some current research, I'm not familiar with them, honestly, because that is not my area of expertise. So, but this is for the presentation purpose. So these are some of them that are listed over here. Okay, so long story short of this slide, so we have to have something that computers can understand. So how many of you know anything about number systems? So computers can only understand what kind of number system? Binary, zeros and one, right? So I have to convert my good stuff that I can understand into something for zeros and one. And this is the one that's helping me. So I have to do it, right? Otherwise, how can I classify? I cannot just say, oh, just cannot say to the computer, hey, this is the human. I need that thing need to identify, okay, what makes it human? So I need to train it. So I have to do all this magic, or I have to do training accordingly, then I have to proceed from there. Okay, so this is the term frequency inverse document frequency vectorization that is again helping us convert whatever website that we have into like a binary format, zeros and one format, so that I can do classification with my machine learning models. Okay. So a lot of math involved here, guys. I'm not going to deep dive into this because again, way beyond my pay scale. Okay. So the data set again that we have used consists of like 450,176 labeled URL instances, like including 104,000 something like phishing URLs and 345,000 legitimate URLs. And then based on these data set, we have trained the model accordingly. Like for example, the data set that we have, the experimental setup was done in such a way that we use something called scikit-learn from Python. Have you heard about this? One of the models that we use to again train and test the thing. So as the experiment says, like it's that 90% was used for training and 10% used for testing purpose. Okay. For this research, specifically what Raymond did, like he gathered the result from the random forest as well as something from logistic regression. So in the experiment that was found, on an experiment when he was doing this thing, so this logistic regression got an accuracy score of 99.787, and with the random forest, slightly better than the logistic regression, is like a 99.867. So as the machine learning algorithm or world say, the more accuracy result that you have, the better your result, overall result will be. So these two, of course, they are in the winner's seat. So that's the reason, or that's the result that we have got. So all this regarding this logistic regression and random forest were all what happened like with something called hit and miss as well. So for example, in logistic regression, we got two legitimate URL incorrectly flagged as phishing and 70 phishing URL misclassified as legitimate. Okay, there's always something called false positive and false negative in the computing science world. That will always happen. You cannot just stay away from it. Similarly, in random forest, 4 legitimate URLs were misclassified as phishing, and then 41 phishing URLs were misclassified as legitimate. So that's completely normal in this case, it's a computing world. So long story short, again, so our machine learning algorithm, random forest as well as logistic regression were into this, achieved a very high accuracy of 99.9, 99.7%, and then we got the best result accordingly. So future work will include evaluating performance in real-time detection environment to test scalability and operational robustness. So that was it from this small research from undergrad student, which was presented by me. If you have any questions, I can happily take it with me and ask you and answer your queries accordingly. So that's about it. Thank you so much. Okay, so that was it, I think, for this session. So I know probably 45
You can give your certificate too.
Okay. Thank you, Dr. Thank you, sir. Okay, so thank you, everyone. So we still have like 30 minutes. We can chit chat or whatever. I'm pretty sure we all are hungry.
Well, dinner will be at 7 p.m. We have 1 hour. Just enjoy. You don't know what's the next.